All right, so welcome everyone. Thanks for joining us on this Friday afternoon. So this is optics and specifically the PER interest group within optics. And as you probably have seen before, we have a very rich website with lots of information. But I just want to highlight the fact that we have a number of events scheduled for the spring. So today we have this session focused on quantum physics, and then on March 14th, April 4th, and April 25th, we'll have three more sessions. One about physics education with games, and another one will be focusing on the learning assistant programs. And then finally, we'll talk about the question of textbooks. How do you choose textbooks and on what criteria and so on. So I hope you'll be able to join us for those sessions. Now, today we have the pleasure of hosting Jim Freericks, who's at Georgetown University. And we invited him to to celebrate the International Year of Quantum Science and Technology, and to try to pick his brain on good ideas to find ways to introduce some quantum physics within introductory physics courses. There are a lot of constraints, but he's an expert on the subject, so I hope we'll get some good advice for him. So without further ado, I'm going to let Jim take over, and then we can, of course, we'll have questions at the end of the session, and then we'll also at the very end, we'll have a very brief participant feedback. We'd like you to contribute at the end. So we'll post that when we're done with the event later. All right, thank you. All to you, James.
All right, thank you very much. It's always a pleasure to come talk to the uh, two-year college group. I gave a talk maybe 3 years ago. It was like toward the end of COVID. I
Mhm.
talked about teaching quantum mechanics in two-year colleges. I actually learned a lot about constraints that are in the two-year colleges that I was not so familiar with beforehand. So I'm going to just jump into this. Let me actually start off by just saying one thing. You might not recognize a lot of the things that I'm going to talk about. These are not things that are difficult or hard. They're just not things that you might have seen before because they're not commonly the kinds of things that you're going to see in an introductory uh, physics textbook that wants to talk about quantum mechanics. Um, Many of the things I'm going to talk to you about are part of this book that I am in the process of having completed. I've just been given the cover, so I'm showing you the cover of this, which is doing all of quantum mechanics without using any calculus. So everything that is done in this is done algebraically, but it does get to some very complicated and advanced material in the process of doing so, even though it does start off in a very elementary fashion. I want to stress when you decide that you want to include quantum mechanics into your course, it's really important that you think about what your learning goal is going to be. And I'm going to give 5 different 1 week learning goals. Some of them will rely upon earlier learning goals. So this would be something if you're thinking about doing it in more than 1 week, or if you want to think about alternatives, if your institution does teach the modern physics class, I am universally of the opinion, and I hope there's no one here who has written a modern physics textbook who's on this call, but I am universally of the opinion that all of the modern physics textbooks are awful when it comes to quantum mechanics. They really focus on the wrong topics and the wrong ideas. So the first, I'm going to just go through each of these. I'll mention each of these, and then I'm going to go into more detail about what content would be included. And then we will hopefully have plenty of time to have additional discussion, which I hope we'll be able to do. So the first one is to explain how single quanta are measured. And in the process of that, you can describe what a photon really is and how to create and test that you have a single photon source. The second one is use the principle of superposition to explain how the quantum mystery works with the two-slit experiment. And this is the question about you see interference when you don't look at the slits, but the interference disappears when you observe at the slits. The third one is explain how entanglement decreases quantum interference and how it can be employed in delayed choice and interaction-free experiments. These are some of the really interesting and super exciting things that you could share with students, but you really would want to do the superposition one before doing this one. Describe how atomic spectra leads to the canonical commutation relation. So we all know that the commutator of X with P is IH bar. Oftentimes that is just given as a postulate, but you actually can essentially derive it. It's really a very strong motivation just by the fact that atomic spectra have sharp lines. And that's actually a very interesting story to share. We have discovered, now mathematically this has been long known, but we have discovered that if you use a decoupling method to solve the classical harmonic oscillator, it immediately provides a really interesting and robust link to how you would treat the harmonic oscillator in quantum mechanics using operators. And it is such that it actually could fit in well with an introductory class that is freely using calculus, because this is going to use some calculus ideas with it. And associated with that one, we also have a similar one that works with Kepler orbits and hydrogen. And in fact, what I'm going to show you in the very brief derivation I'm going to show is what I think is the absolute easiest way to get to Kepler orbits. The one thing that people shy away from in doing this is it does require you to work with complex numbers. And oftentimes it's viewed that complex numbers are forbidden in a first-year class. I think that's an unfortunate choice, but most textbooks do operate under that philosophy. And if that is something that you also want to stick with, then those would not be topics that you would want to try to use. All right, so how single quanta are measured, what a photon really is, and how to create and test that you have a single photon source. You would start with doing something like the tutorial from Introductory Physics on the photoelectric effect, which is if you've never seen the tutorials in Introductory Physics, this is a really, really good one that helps explain how the photoelectric effects works and how to understand what the photoelectric effect is. You then have to talk a little bit about atomic physics in noting that there are, trying to find the laser pointer. Is that the laser pointer? There it is. You need to know about energy levels in an atom, and this is the original single photon source. It's called a calcium cascade quantum source. It requires two lasers to excite from an S state to an S state, and it then decays via a two photon transition where the second transition occurs within a nanosecond after the first transition. And this is called a heralded quantum source because you can observe this photon and then you know a second photon is about to come out. And when you do that, this is an experiment that is set up. The source would be sitting down here in this region, and you'd have a parabolic reflector, so everything would come to your detector, which is sitting here. And what you would find is you have to wait some delay time, the time it would take a photon to travel this distance. And then because this is a probabilistic decay, you would get the characteristic exponential decay with a lifetime seen in the signal. And this is something that is directly measured. And then the next thing you would talk about to show that it really is a single photon source is what's called a G2 experiment. And for that, you take your single photon source, you put it on a beam splitter, and behind the beam splitter, you put two detectors, and you know when to turn the detectors on because of the heralded light source. When you see this photon, you say, okay, now I'm going to take data. You wait about a nanosecond or so, and you ask, was it observed in detector 3 or detector 4 or in both? And by looking at the ratios of how often you see single detections versus double detections, you can measure this thing called the G2 measurement. Here it's called alpha. And when that's less than 1, then you have a single photon source. If you were to do this experiment with a dim laser, you always get a number that's bigger than 1 because dim lasers are never single photon sources, even though you'll find many textbooks that will say, if I dim a laser enough so there's at most only 1 photon in the experiment at any given time, then it will act like a single photon source. The problem is often when you try to do that, you will get two photons instead of one in your apparatus, just because that's the way lasers work. And so it won't really work exactly like a single photon source. And the main thing about a photon is that it can be measured once and only once. And that's another idea that you could convey if this was a topic that you wanted to talk about. The next one I'm going to talk about is the principle of superposition and how to explain how the quantum mystery works with the two-slit experiment. When I teach this, this is based on Feynman's QED book, where you draw different paths, different alternative ways an event can occur. Each way has an arrow that's associated with it. They have slightly different times, which correspond to the different directions of the arrows. You hook them head to tail. You get a final arrow that you square, which gives you a probability, and you get probability distributions that look like this for a single slit, which is giving you the nice single slit diffraction type pattern. You can do similar things with two-slit experiments, which I'm going to show you in a minute. So here's single slit versus two-slit. And here's the classic building up of the pattern with single photon sensitive detectors that can detect individual photons and eventually show that you build up a pattern, even though it looks totally random at the beginning and you don't see the pattern. We also have a lot of materials that work with two-slit experiments, and we talk about what happens when you put detectors in versus you don't. Mm-hmm. You can see here the kind of image you would get if you were observing them a single photon at a time, and this is the kind of probability curve you would get for a two-slit experiment. And all of these animations are freely available. They run off of websites, and so you can get and use these if you want to. The next topic was explain how entanglement decreases quantum interference and how it can be employed in delayed choice and interaction-free experiments. The best way to do this, which is actually the best way to show detectors at the slits, is with cross polarizers. So if you put a vertical polarizer on one slit and a horizontal polarizer on another slit, and you send in diagonally polarized light, then you have tagged the photon going through either slit. And then if you measure, you will see no interference pattern. But if you put a diagonal polarizer before you measure, the interference pattern will come back. And this notion that entanglement reduces interference effects is one of the critical ideas to understand about entanglement, especially if you want to talk about things like decoherence. You also can talk about experiments such as an interaction-free experiment. This is using a Michelson-Morley interferometer with polarized light and a polarizing beam splitter, and you rotate the polarization so that very low probability of photons go along this path. But if you put an obstruction on this path, the photon that would go along this path would get absorbed. But because you're using a single photon experiment, the probability of that happening is actually fairly low, and you can detect whether or not you have an obstruction on this path with a photon that never actually goes on and hits the obstruction because it's using quantum interference effects. And this is like a really cool kind of experiment that's a modern experimental idea that you won't find in most textbooks, but is a really cool thing to talk about. And it all follows with this sort of Feynman type way of treating these problems and requires nothing more than high school algebra to do these things. Many of these ideas can also be demonstrated using simulations on quantum computers if you want to go that route. If you wanted to teach a little bit of quantum computing, you can actually use quantum computers to demonstrate and illustrate many of the ideas in those experiments, which really are single quantum experiments. Okay, the next one is describe how the atomic spectra leads to the canonical commutation relation. This one does require doing some algebra with operators, so it has a little bit of abstraction with it, but I'm going to take you through it relatively slowly so that you can see how it works. It starts from the idea that atoms have sharp lines. It uses the Planck-Einstein relation that the energy is equal to h bar times the angular frequency. It uses the Bohr idea that transitions in atoms occur between stationary states that have definite energy. includes the Heisenberg idea that the matrix elements oscillate harmonically at a frequency given by their energy difference. And it uses the idea that the total energy is kinetic plus potential. And the way that it works is you have to introduce the idea of operators. If you like, I can elaborate more on how that can be done, just starting from atomic spectra. You get to the notion that matrices are the things that you should be looking at. This is what Heisenberg came up with. And if you talk about matrices, you can then talk about operators as an abstraction of the Hilbert space from a concrete representation as a matrix into an abstract representation in terms of operators. But you would have your two states that have definite energy, states M and N. You evaluate the commutator of a Q operator with H. Because these are eigenstates of the Hamiltonian, you can let the H act on each of the states. You get En minus Em. And you can use Planck-Einstein to relate that to minus h bar omega mn, with omega mn being the frequency difference between those two states. Now, these matrix elements go like e to the I omega mn t. This is Heisenberg's idea that they vary harmonically with a frequency, and the time derivative of that is proportional to the frequency. So this object is proportional to the time derivative of the Q operator. And that is, of course, just P over M. So I get that one way of evaluating this commutator is that it's equal to IH bar M, P over M, this matrix element Mn. We also can directly calculate the commutator. The commutator of Q with P squared over 2M can be evaluated using what's called the Leibniz rule, or product rule. It's P times the commutator of Q with P plus Q commutator of Q with P times P. And then I have a commutator of Q with V of Q, but because Q must commute with V of Q, this commutator has to equal 0. And if I assume that this thing is a number, I can collect these two terms into one term. And you see, it's the same thing as this, and you can equate the coefficients. And that's what gives you commutator of Q with P is IH bar. Now, I do want to mention here that this may look frightening to think that you would present this to freshmen in a classroom. So yes, it would require some scaffolding to get to the point where this is stuff that they could understand. But it doesn't actually take that much to get to the point where this is something that they could understand. And you can see it's essentially a derivation of the canonical commutation relation, which I think is a really cool thing, so that students don't have to just be told that's what it is. It essentially is coming from those ideas that I had presented earlier. Okay, so you can actually say that it's experimentally motivated and not have to do the thing that appears in many textbooks where they say, we just assume it's true, we do our calculations, they agree with experiments, so that's why we do it. All right, so now I'm going to do something that is a little bit advanced mathematically, but it's not super advanced. However, it does use complex numbers. And if you do not want to use complex numbers with your students, then this would definitely not be appropriate. But if they are students who have seen calculus, and you only need to have seen differential calculus, this is a topic that can be done. And I think it's a really compelling way of bringing quantum mechanics. You can see it emerging from classical mechanics. So the idea is we start from the Hamilton form of the equations of motion. They don't need to know anything about Hamilton or Hamilton dynamics in order to do this, because the equations are x dot is P over M and P dot is the force, which for our harmonic oscillator is minus M omega squared X. We then use the mathematical trick, which says we can decouple these two coupled differential equations by taking a linear combination of the two terms. So we're going to form this object we call capital A, that is P plus alpha X. We're going to take the time derivative of it. So that's just P dot plus alpha X dot. I just come here and substitute in what P dot is, substitute in what X dot is. I get minus M omega squared X plus alpha P over M. I'm going to factor alpha over M out because I want it to be proportional to A. And I know that A has a P in it. So I'm going to factor alpha over M out. And I'm left with P minus M squared omega squared over alpha times X. For this to equal A, the coefficient alpha has to equal this thing. So you just set them equal. Alpha equals minus M squared omega squared over alpha. You can solve that. You get alpha is plus or minus Im omega. And then
Um,
you can see this coefficient is plus or minus omega, plus or minus I omega.
like
So
getting,
now,
nobody's ever gotten angry like that, especially on
so I
television.
think
Well,
someone, Nancy, you might have to mute. Thank you. So A dot is then equal to minus I omega A. There's similarly the complex conjugate A dot star is I omega A. Now, this is a differential equation, but it is so easy to solve because it's just solved by the exponential. People don't need to know anything about differential equations to solve this. They just need to know the derivative of an exponential is proportional to the exponential. And then you can solve it as A0 e to the minus I omega t and A0 star e to the I omega t, with A0 just the initial value of this, which is P0 minus Im omega x0. And now, because I have an A that has P plus I alpha x and the A star is P minus I alpha x, I can solve for the x by just taking the difference of the two. So A star minus A divided by 2Im omega gives me x. And if you plug that in with these solutions, you get x0 cos omega t plus P0 over m omega sine omega t, which is the standard result. So it's a really nice way of getting that result if you're willing to introduce complex numbers. And now here's the beautiful connection with quantum mechanics. Oh, first I'm going to tell you about the energy. So if we have the A and the A star given by this, let's just look at the product of A times A star, and I'm going to divide it by 2m. You can see it's going to give me P squared plus m squared omega squared x squared, and then it's going to be divided by 2m. So I get P squared over 2m plus 1/2 m omega squared x squared. That's the energy. But of course, you see here, the exponential terms will cancel. So it's just mod A0 squared, which is a constant. So you immediately get energy conservation. And I think that's really beautiful. No difficult calculation at all to get energy conservation. Now, knowing that that's the energy, we now go to quantum mechanics. We let these things be operators using commutator of x with p as IH bar. So we define this thing A, which is p minus I m omega x, all operators now. We form 1 over 2m A dagger A. We'll get p squared. We'll get the m squared omega squared x squared, and then we get an extra term which comes from the commutator. But it's easy to evaluate. You just substitute in the IH bar, and you get this constant. And if I bring it to the other side, you see you get that the Hamiltonian is 1/2, 1 over 2m A dagger A plus 1/2 H bar omega. It immediately gives you quantum mechanics from an exact analog from the energy relation in classical mechanics. And this is a recent work that we've just finished. It's actually not in the textbook that I was showing you earlier. But I think it's a really cool way of making a connection between classical mechanics and quantum mechanics. And then we can do the same thing for Kepler orbits. Here, of course, it's a little bit harder because we have both the radial and the angular degrees of freedom. But these are the equations of motion that you have. And important is there's no angular force, which means angular momentum is going to be conserved. So L is equal to mr squared theta dot is a constant. And then we have to come up with the right ansatz. This is the right ansatz to use. PR plus alpha over r plus beta. We just do the same thing. We take the time derivative. We substitute in what PR dot is. We substitute in what R dot is. And so that's what this expression is. We factor out what lies in front of the PR. And then we have to force this to equal the thing that we guessed. So this coefficient here has to equal alpha, and this coefficient has to equal beta. You get an equation for alpha, which is going to, again, involve a complex number. You find alpha is plus or minus IL. You find beta is minus plus IMK over L. And then because alpha is I plus or minus IL, L over mr squared is just theta dot. So you find A dot is minus plus I theta dot A. I can also write that instead if you, well, I mean, this can be immediately integrated as A0 e to the I theta. You can think of it as theta of t, or you can just think of it as the theta coordinate. Okay, because the derivative of this with respect to t is A0 I theta dot e to the I theta, just by simple calculus. So it's a very simple differential equation to solve. You also get the similar equation for A star. And now we want to isolate the terms that depend on 1 over r. So we're going to, again, take a minus a star. We're going to set the a0 by looking at the closest approach where PR is 0 and the closest approach is R0. And then we just solve for 1 over R by taking this difference again divided by 2IL. And this is the orbit equation. You can simplify it, but this is the simplest derivation I've ever seen for the orbit equation. No complicated integrals of any kind, really just a handful of lines. You might even want to consider doing this in your regular treatment of the orbit if you do derive the orbit in your introductory class. You also can get energy conservation from this in the same fashion. If you calculate 1 over 2m a star a, this part here is the energy, and there's an extra constant. So you just have to bring that constant to the other side, and you get energy conservation, again, in just like a one-line derivation. And to go to quantum mechanics, we do the same thing. We introduce R and PR. They have a canonical commutation relation. We calculate 1 over 2m a dagger a. This calculation is a little bit harder to do, not super hard. You get this as the final result. And if we let L equal H bar L plus 1, this is actually the quantum Hamiltonian for hydrogen. And you can read off the energy levels from it as well. So it's you actually have to just move the constant to the other side, and you can get the Hamiltonian for hydrogen as well, just by doing a little bit more than the solution that you do for the orbit equation for the Kepler problem. So many of the ideas, but not all of them, are in this new book that I have, which is called Quantum Mechanics Done Right. It's forthcoming from Springer. The electronic version is going to be free, so it is an open access book. The first 4 chapters cover conceptual ideas. The next 8 cover formalism, and the remainder of the book gets actually quite advanced. It does use no calculus, no math more complicated than high school algebra, geometry, and trigonometry. It does do a little bit of linear algebra, but all of those mathematical ideas are fully developed within the text. And I was just given the cover, draft of the cover yesterday, so that's what it's going to look like. And I think that's all that I have. So those are just some of the ideas that I have. Now, one question you might ask is, how come I didn't talk about spin and Stern-Gerlach? There's a very specific reason why I did not talk about spin and Stern-Gerlach, because in order to describe spin and Stern-Gerlach, you need to know what the force is on a current loop. And that is actually a pretty advanced concept that's hard to follow. You also need to really be well-versed in precession if you actually want to understand what would happen to a current loop if you put it in an inhomogeneous magnetic field, to understand why you get a splitting. So if you want to explain that, I actually think that's a little bit harder to do and might take more time than some of these other things that I have shared with you, which I think build off of many of the concepts that you have already taught students in the class. And I do recognize that some of them are a little bit more advanced, some of them are a little bit abstract, and it all depends on whether you're teaching a class that is including calculus or you're teaching a class that is purely algebraic, as to what kinds of ideas you might want to put in and which ones you definitely should not put in, because it won't go well with your students. But I also wanted to stay away from what is the standard thing, which is we're going to give you some numbers and let you calculate sizes of things like the electron and other stuff like that. I don't really believe students get much out of those exercises, even though they can do those kinds of problems. And I'm not sure that they really learn a lot about what quantum mechanics is. I think if you do things like teach them what a photon is, that can be measured once and only once, that creating a single photon source is a difficult thing to do, and other things like that, they get a lot more out of that than some of these other kinds of more traditional quantum exercises that you'll find in introductory textbooks. So that's all that I have to say, and happy to have more discussion. And if you don't like any of my ideas, happy to talk about that as well. Especially if I miss the mark on some things where you're like, oh, you guys, there's no way my students are going to be able to do that. I'd like to hear that too. And maybe I'll even might convince you that maybe it's not as bad as you think, but I could be wrong on some of those things as well. I'm happy to hear what you guys have to say about it.
All right, thank you very much. So anybody has a really quick question you want to get to right away? And as you can go ahead and unmute if you want and jump in. I was going to ask you, for many of those you mentioned have a website with a simulation. Are those do they provide some sort of tutorial on, just running the simulation or something that could be immediately used, or is this something that instructors would have to write for their own students just to briefly walk them through the basic steps?
So I don't have like handouts, if
Okay.
that's what you're asking, because I haven't been doing these projects that I've been working on as curriculum
Yeah.
that I would be handing out to people to use. But all of the materials are part of a course that I have on edX called Quantum Mechanics for Everyone.
Mhm.
And all of the exercises and discussions and stuff are all embedded in there. And so one could actually extract from that materials that you might want to use for yourself.
Okay.
All of the animations and stuff, they're all written in JavaScript and they're intended to run in an iframe. So you can actually go to the GitHub site, download them,
Mhm.
and set up a website with an iframe for your students and let them go and do it.
Okay.
If you want to go to, I'll put it in the chat.
Yeah, that'd be very useful to have.
I will put quantum.georgetown.domains.
All
If
right.
you go there, and I can actually go there and show you. This is my quantum mechanics site. There's, you go to courses, course for everyone. And this is a collection of videos and a collection of the tutorials. So this is one of the tutorials. You can just click on it. Oh, nope, that's the video. Sorry. This is the tutorial. I don't believe you're going to break my website if you sent your students here.
Okay.
You can just run through the tutorial here. So here we're introducing, this is after a lot of instruction, by the way. You might not want to start with this. We're introducing a source of current loops. There's some text that appears in here that tells you what's going on, but you can see it's really beautifully animated the way that you can see the current loop, and then the arrow is pointing in the direction of the effective magnetic field that is created by that current loop. We look at, it's going to send them out in different orientations. Oops. And here we're going to put it in an inhomogeneous magnet. We're going to track how it goes through the magnet. It feels a push, and it's going to hit the screen according to the push it feels. We then can change the orientation. It feels a different push. And changing it yet again. This one feels no push. So it goes straight across. Then we do a highlight to show you exactly how this works. This is a current loop coming in at an angle. It processes as it goes through the magnetic field, but also feels a push. And that push is going to get magnified and eventually hit the screen at a particular location. And then we look at what happens if we look at a number of different angles. And classically, what you will get is a buildup of a full pattern.
Right.
And so this is what these kinds of animations look like. And we have exercises in the course that follow and complement these. So you'd have to do a little bit of work. It's not like something you just grab and immediately go with, but these materials are free and available to use. Um, and I'm happy to share them. There's
Yeah.
about 50 different animations and simulations that we have in this collection. So there's quite a bit of stuff.
Yeah. Well, in fact, one of the motivations for the session was to maybe give some ideas to people who would like to do something about this, and maybe either use something that's ready to go, or like in this case, develop their own little activity around something that's already available online. And then that'd be really, really good exercise. And I got myself thinking at this point, so things I can.
And I am happy to, you know, bounce back and forth ideas if you want to talk with me about it or send
Yeah.
me email about it. I'm happy to give you some ideas about it. That class, I've had lots and lots of high school students who've taken that class and covered the material in that class. And you can cover quite complicated things. We talk about the Bell experiment. We talk about delayed choice experiments, really complicated modern quantum ideas that you won't find in most textbooks. And it really requires like absolutely zero math of any kind aside from things like high school algebra and trigonometry. And
Yeah.
even that doesn't really require very much.
Yeah. Yeah. One of the ironies is that we're celebrating the 100 years of quantum physics, and yet we still keep that for later courses, and we don't introduce that very early in the curriculum. So I'm not sure when that's going to change, but maybe this is a good. I mean, it's been
I
100.
think it's really nice because, frankly, you ask a student, what is cooler, being able to see something without shining light on it or a block sliding down a plane? I mean, that's a kind of a no-brainer, which one is cooler. And it really can excite people to talk about some of these ideas. Some of them you don't really even need to leave until the end of your class either. Some of these ideas you could incorporate, like if you were talking about harmonic oscillator, this would be in a class that you have with students that are doing it in a calculus-based sequence. You could do things like what I showed you. You would have to introduce some discussion about quantum mechanics and why we have operators and things like that. So I would recommend actually doing it after you motivate what the canonical commutation relation is. But you could kind of incorporate it in at a similar time in which you're teaching the classical mechanics ideas rather than just waiting till the end.
Mhm.
Or you could teach the classical mechanics ideas using things like the way I showed how to do the harmonic oscillator. And then you could return to it, refresh their memory when you wanted to talk about quantum mechanics later. That's another option. But again, it does require introducing complex numbers and having your students work with complex numbers, which, according to the modern introductory books that I see, is viewed as a forbidden thing that thou shalt not do. I think that's doing a disservice to our students. I think with proper instruction, they could probably follow. Most of them know Euler's formula. That's really most of what you need to know in order to be able to work with complex numbers. So I don't think it should necessarily be so forbidden, but if you're forced into that kind of forbidden land, then that's not something that you'd be able to do.
All right. Anybody else wants to jump in the discussion? It's something that you're curious about. Has anyone else done any kind of introduction of quantum elements in their courses at this stage? Or? I know it takes a lot of preparation to be able to do something.
Yeah. Is the book going to be, when is it going to be available online?
The book I am hoping might be available as early as the summer, but I'm not completely sure. So I submitted it in December. I think they really only started working on it like a couple days ago. They gave me the draft of the cover, which is what I shared with you. I know it will be at least 6 weeks after they send me back the proofs before I will be able to turn them back over to them. But if they only take like a month to get the proofs to me, then yeah, then I think it's highly likely it'll be available in the summer.
So
I'm hoping it will be, but I don't know.
will it be structured like a textbook with like text and exercises, or?
It does have text and exercises
Thank
all
you.
throughout, yes. And it also has lots of links embedded in it. So there are links to videos, there's links to all of the simulations. It's all embedded in it as well.
Okay, good.
I just have a question about the website that you were sharing.
Mhm.
I see there's a tab or like a couple tabs. Is the everyone tab, is that kind of material that you developed kind of for the edX course I think you mentioned, or
So I have 3 edX courses, and they're all
okay.
actually on that page. One of them is a math methods, one is quantum for everyone, one is an undergraduate quantum. I actually use all of the material in quantum mechanics for everyone in my undergraduate quantum mechanics class, because I think students need to understand how to think conceptually about quantum mechanics, and we don't teach that. And this is a way that you can actually reason conceptually about quantum mechanics. So even though I originally developed it as a course for non-scientists, I actually use it with my majors as well.
Okay. And so, yeah, I'm just doing like like, I'm not reading carefully. I'm just kind of skimming, but
Yeah,
the
yeah,
undergraduate tab is that kind of like for your, like your majors level courses, like your
that's
intermediate?
right. Yeah, that's a
Okay.
junior
Okay.
level class. That's a junior level class that we
Okay.
teach. It's a
Okay.
1 semester junior level class. And that class is not a class that's taught without calculus. It doesn't have a lot of calculus in it, but it does have some. And all of the students would have taken the math methods class before the quantum mechanics class. So they're all familiar with a lot of the traditional things that are taught in a math methods class. So linear algebra is not something that they're afraid of, and other things like that.
Just really quick follow-up. I see that the videos for the majors level class, I think, or at least it says it's mentions it's in YouTube. The ones in the everyone tab, are you okay if we utilize those in our
I mean,
are these videos or
it's going to just link to YouTube.
oh okay, oh these are just YouTube links. Okay, so
Yeah, everything is on
okay.
YouTube. I have a fairly big YouTube presence. If you want to find out more about the book, I have about 35 videos or so summarizing different parts of the book that are already on YouTube, on a YouTube channel. You can go take a look at those as well.
Yeah, I saw that, but I didn't want to take a dive yet. So I saw there was a long list of videos, and I said, "Ooh, okay, that's for later." Spring break's coming up.
Yeah.
Okay, thank you, thank you.
Okay.
Again, I just want to emphasize, if you do decide you want to teach quantum mechanics to your students, give them some flavor of quantum mechanics. I think it's really important to take some time to think about what it is you want them to actually learn.
Mhm.
And come up with that learning goal first. And after you have the learning goal, think about how to design the curriculum that you want to support the learning goal. And that's really the critically important thing. You know, what aspect of quantum mechanics do you think is the cool thing that they should learn about? If you think it's superposition, then that would kind of tell you what direction to go. If you think I want them to understand where the canonical commutation relation comes from, then that's something that would steer you in a different direction as to what it is that you might want to use.
So,
I
so
have had instructors use the simulations not in the way that I use them, where the students work through them, but instead use them in a form where they're actually using them as part of the lecture. So they will kind of go through them similar to the way that I did it with you, and kind of explain what's going on with the simulation as part of a lecture, which is another perfectly fine way to use them.
Nancy, I see you have your hand up. You want to jump in?
So I'm sorry, I missed the very beginning because I got the time mixed up. And maybe you already addressed this, but for many of us teaching the freshman level introductory classes, we're teaching a lot of topics. Is this a course? It's pretty much the whole semester is on quantum mechanics, or is just a piece? of a semester? And if
Again,
so,
so I'm not suggesting necessarily if you're teaching an introductory class to go and do those 5 or 6 things that I suggested. I was just giving you ideas for what could be a 1 week insertion into an introductory class that would be, as opposed to like a overview of quantum mechanics in some fashion, or a discussion of the historic experiments, which I don't think the students get much of anything out of. Instead, picking a focused idea and trying to convey that and the beauty and wonder of quantum mechanics associated with that idea. And so teaching about how do I measure something that's so small I can't see it. I think that's a really cool idea to bring in and do as a 1 week course. And then you could teach them what a photon really is, and they won't just say it's a particle of light. They will understand it means that it can be measured once and only once. And single photon sources are not just dim light. They actually require a complicated physical system to create a single photon source. If you do that in 1 week and the students actually get it, I would say that's fantastic. You really taught them something important and critical about quantum mechanics. Or you might say, I want to teach them about superposition and the 2-slit experiment and how the superposition disappears when I observe at the slits. Well, that's another thing. That's another thing that you could do. You could choose to do that over a week. Maybe you say, I want to do 2 weeks because I want to also talk about entanglement. Well, then you can do like 2 weeks in a row, one on superposition and then a second week on entanglement, where you can then talk about even more complicated and crazy kinds of ideas that come up. So these were just different ideas of things that you might want to do. And then the sort of last 3 that I covered, I was thinking more in that case about, there's some of you who might be teaching modern physics classes. And if you're not satisfied with the modern physics textbooks, which I think are about one of the worst kinds of textbooks I've ever seen in my life, I do not like the way that they cover modern physics ideas. So when I teach modern physics at Georgetown, I don't use them at all. Those are ideas that you could think about incorporating as a different way of doing quantum mechanics in a modern physics classroom. So I was trying to cover both of those different areas.
Now, I was thinking, let's say you want to bring the students to maybe some appreciation of the, all the news they hear about quantum computing or something like of that sort. What would you recommend as like 1 or 2 ideas that would be kind of good to expose them to?
Well, I would think about doing it over a 2-week period.
Okay.
In that case, and I would pick one of the ideas like the 2-slit experiment.
Mhm.
I would cover that in the first week. And then in the second week, I would simulate it on a quantum computer. I would teach them what they need to know about how to simulate it on a quantum computer. Now, it's much easier if they know Python in order to do that, but IBM does have a kind of setup where you can just pick quantum gates and put them into a circuit. And I can share with you, I have a paper where we're about to submit this paper, which talks about how to do this for a Mach-Zehnder interferometer. Now, the challenge is it's difficult to do this and have them run it on a computer as like a homework exercise or something, because sometimes the queues take some time to get through and run, and they can be, everyone has to sign up for an account. Sometimes installing the software and getting that to work is not so simple. But here we're talking about Mach-Zehnder interferometer, which is very similar to a 2-slit experiment because you really have these 2 different paths that the photon is taking. This is a circuit that simulates a Mach-Zehnder interferometer. So this is the first beam splitter in the mirror. This is a a NOT gate or a X rotation. This is something called a Hadamard. This is a Z rotation. This applies the phase difference on the two paths. This is the second beam splitter, and then you have a measurement. And so you could actually develop teaching quantum computing not the way computer scientists do it by here are some different algorithms that show how quantum computing could be good, and then it's usually applied to problems that are kind of made up problems like the Deutsch-Jozsa algorithm or something like that. Here you can say we're going to use a quantum computer to simulate a single photon Mach-Zehnder interferometer or a single photon two-slit experiment. And you can go ahead and run this. You'll get data that looks like this. I mean, it's almost perfect.
Mm-hmm.
But this could take more than a week to run.
Yeah.
That's the one problem with it. It takes some time to run. And then you can do more complicated things as well. So there are a lot of things where you can think about trying to, the problem is no one has created the materials yet where you can just grab them and go at the moment. Maybe in a year or two that will be more readily available, but they're not quite available yet. You could have them run on the simulator instead of running on the quantum computer. That they can run immediately. Mm-hmm. But in my opinion, that kind of defeats all of the fun of saying I actually am using a quantum computer if I'm just using a simulator. Yeah. But this is the challenge. IBM is making them freely available, but they're fairly heavily utilized. And so you can't for sure get access to them and make sure that your students could just use them. Yeah. And for sure, you can't get on a lecture and say, we're going to make our circuit, we're going to run it, and we're going to see what the results are, because it won't necessarily run during your lecture. Yeah. You can say, I did run it, and here's the results that I got, and so forth. But you can't really do it in a way that they would be able to see it in real time at this stage. IBM used to allow that, but they got rid of that program.
This would also be pretty good for a special project, like students wanting to do either some kind of independent project.
That is correct. Yes.
Yeah.
It would need to be more than a week long, but yes, if you wanted to do some kind of a special project, especially if you covered like some of the topics in, like you did a 1-week lecture that covered some of these topics, having a special project where they tried to do the simulation on the quantum computer could be a really nice thing to do. Yes, I agree.
Yeah. Well, this is the year to do it. It's 100 years since we've been talking about this stuff. All right. Do we have anyone else who want to also have a question here? So you gave us a lot of things to think about and options also, which I think was really
Let me put my email in the chat too. I'm more than happy to talk with people about these ideas if they would like to.
Okay. Yeah. In fact, I'm thinking that if somebody did put some sort of activity tutorial for, TYC, it probably would be very popular with instructors. Somebody would have to do a bit of the legwork to get it all together and then share it. I think that'd be an interesting project. Not that I'm volunteering, but
I'm not sure. I'm not sure that I have the bandwidth to do it myself. But if someone wants to volunteer to do that work, I am happy to help them with materials and other things like that. So if someone wants to partner on that, I'm happy to.
Okay.
Share in the labor of that.
Yeah. Okay. Well, that was great. Let me. I think we are just about within time here. So I want to thank Jim one more time for, first of all, agreeing to, responding positively to my request, my invitation very quickly. So really appreciate that. I also wanted to ask the participant here if you could take a minute and share with us your feedback on the event for today. So the link to it is right here. If you can, and I'm going to also maybe copy it here and put it in the chat.
And Tom, I don't know, do you want to announce this workshop?
Well, Jim is going to be doing a workshop at the tandem meeting this summer on, which is on Saturday, August the 2nd, with an association with the APT summer meeting.
Okay.
So some of you would like to attend a tandem meeting. Jim will be one of the workshops there.
So that would be like a half-day workshop, or how's that gonna?
The workshops are like 1 3/4 hours long.
Oh, I see that. Okay.
And if you're not familiar with the tandem meeting, basically it's a 2-year college focused meeting, full day meeting that is held in conjunction with the AAPT summer meeting.
And it's going to be, should we mention also that it's going to be in DC this summer? Is that right?
That's
Yes.
correct.
Okay, so just to let people who may want to be thinking about maybe attending the meeting. And of course, you'll get plenty of information about that eventually. But if you're on our mailing list, you'll get some information about that as well if you visit the Optics website and AAPT in general. So I'm pretty sure you'll hear about this. Well, it's 3:58. I think it was a pretty interesting conversation. And anybody wants to have a few words to finish? Otherwise, I will thank everyone for coming and wish you a good rest of the day.
Thank you.
Thank you.
Thanks, everyone.
Thank you, James.
Thanks.